This series is the sum of reciprocal primes, and the denominators are all the primes, 2, 3, 5, 7, 11, and so forth. And the question is, does this series converge to a number, or does it diverge to infinity? In this video, I'm going to share a delightful proof that this series of reciprocal primes actually diverges. And I'm going to be able to do this just using some standard tricks from first-year calculus. In particular, I want to contrast this series with two other more familiar ones, the first of which is the harmonic series. This is the sum of 1 over all of the integers. That is, the harmonic series has the primes in it, but it's got a whole bunch of other things. So the reciprocal prime is certainly smaller than the divergent harmonic series, but that doesn't tell us anything about reciprocal primes yet. In contrast, the other really famous series from first-year calculus is the geometric series, and it has expressions like 1/2, 1/4, 1/8, 1/16, and so forth. And I can compare these two series as well, like they both have a half in it, and then 1/3 is a bigger number than 1/4, and 1/5 plus 1/7 is certainly bigger than 1/8, 1/11 plus 1/13 is bigger than 1/16, and so forth. The reciprocal primes are bigger than a geometric series, which does converge. So our reciprocal primes is sort of sandwiched between the harmonic series that diverges, the geometric series that converges, and we don't know where those reciprocal primes are going to land. I can clean up my long expansions with summation notation, where here by pi I mean the ith prime number, and for the geometric series I had previously used x equal to 1/2, but I can talk about it a little bit more generally. Let's input the harmonic series into Maple Calculator, and we can see that the calculator shows us that it does diverge. But what I find interesting is that it actually diverges really slowly. For example, if I plug in 100 for the upper bound as opposed to infinity, it's only a number like 5. And if I went even further and put in like 1,000,000, this only adds up to 14. The harmonic series diverges, but it diverges slowly. My thanks to Maple Calculator for sponsoring today's video. More about them at the end. Alright, so reciprocal primes we don't know about, harmonic series we know diverges, and for the geometric series, I can actually say more when it converges. Namely, if x is less than 1, then this converges to 1 over 1 minus x. I know the value that it converges to. So let's begin our proof. Let's start with the assumption that the reciprocal prime series actually converges, and I'm going to argue by contradiction. If it converges, let's say it converges to, I don't know, 1,000,000, then at some point there is a value n where the terms from n plus 1 all the way to infinity are smaller than the number 1. Like, for example, suppose the sum of the reciprocal primes converge to 100, just to make up an example. Then at some point you would have gotten to 99, and all the remaining terms would be the ones that were less than 1. So regardless, we have some value of n where this series is less than 1, and whatever that number is, some number less than 1, I'm just going to give it a name. I'm going to call it x. Okay. So now let me make a new series for you. I'm going to consider the series x plus x squared plus x cubed plus x fourth. This is a geometric series. And it's a geometric series that is a convergent geometric series because the value of x was less than 1, which we had just argued meant that the series would converge. It's a strange series. Like, each of these x's is itself this infinite series. And then I'm taking powers of those x's and making a new series out of that. Just as an example, let's imagine n was 3. It's probably not, it's probably way bigger than that, but suppose it was 3. So that would mean 2, 3, and 5, the first 3 prime numbers, we're going to throw out. And then I'm just going to consider my sum x to be things like 1/7, 1/11, 1/13, and so on. All of those reciprocal primes not including the first 3. Okay, so now let's take a look at what our geometric series is where we take powers. Well, it's going to be long and messy, so I'll put something up like this, and I'll include that ... in every one of those bracketed expressions that we raise to a power. So this is a very weird object, and I want to try to understand, like, what things are actually inside of this particular object. For example, take the number 1 over 539. Is that in this series somewhere? Well, 539 has a prime factorization of 7 times 7 times 11. That is, it's 3 primes multiplied together, and all of those primes are over the threshold that we talked about. They're all 1/7 or larger. So that number of 1 over 539 occurs somewhere in this expansion, the cubed expansion here, where you're choosing 3 different numbers and multiplying them together. So yes, 1 over 539 is in the expansion. Okay, what about 1 over 538 then? Well, the prime factorization of 538 is 2 times 269. 269 is a prime number. It's somewhere in the dots there, but there's nowhere where this 1/2 factor is ever going to occur. So 538 is not in that expansion. That is, what I'm really considering is the reciprocals of all numbers, where when you take their prime factorizations, all of those factors come from the n plus 1th prime, the n plus 2 prime, and so forth. Okay, so a lovely property, not yet clear how this is going to help us. Next thing I want to talk about. I want you to consider the following expression. 1 plus the product of all of the primes, the first prime, which is 2, the second prime, which is 3, all the way to the nth prime. This is a kind of funny object. The first thing I want to note is that it is not divisible by any of the primes less than n. Let me just try to divide out by, I don't know, say the first prime, p1. Well, at the front, I would just get 1 over p1, and then the p1 would cancel the p1 in the expression that has a lot of primes multiplied. You'd be left with p2 down to pn. p2 to pn is an integer, but 1 over p1 is not an integer. This is not an integer. It's not divisible by p1. Okay, so let's return to the expression. And actually, this is true if I then multiply an I out the front. If I put any multiple of that p1 down to pn, it's just not divisible by any of the first n primes. By the way, if you see my video proving that there's infinitely many prime numbers, you can go and check that out, then you'll notice that this basic expression is one that we had to use in that video as well. So this is kind of returning to us. Regardless, what this means is if I try to figure out what is the prime factorization of 1 plus I p1 down to pn, well, that is something like the things we were just talking about. Something coming from the n plus first prime, the n plus second prime, and so forth. 1 plus I p1 down to pn has no prime factors in it that are less than n, so all of them must be more than n. Okay, so I think I've collected all the random tools that we're going to need in our proof, so let's put them all together. I want you to consider the following new series. This is the sum, from 1 to infinity, of 1 over 1 plus I p1 down to pn. 1 over those expressions that I was just talking about. My claim is that this series is a sub-series of the x plus the x squared plus the x cubed that we were talking about, which we had argued was a convergent geometric series. What do I mean by a sub-series? Well, all the terms in the sub-series occur in the main series, but the main series might have even more terms. And indeed, what we had just spent all our time arguing was that our denominators of this series looked like the type of the objects that were in the geometric series, the x plus x squared plus x cubed series. So indeed, everything in this new series I'm talking about would have shown up in the geometric series. This is a subseries. Okay, so let's analyze that subseries. When I look at this, I think when n gets really large, the plus 1 is not going to really matter. When I look at the p1 out of the pn, that's just a constant multiplying by the I. So when I look at this, heuristically, I just see 1 over I. The constants I sort of know are not going to matter, and I'll be precise about this in a moment. When I look at the top series, it looks like a harmonic series that I know diverges. Okay, let me be a little bit more precise about how I can compare this more complicated one on the top to the harmonic series. If I just consider the terms, let me consider their ratio, and I'm going to do something called the limit comparison test from calculus. I have a video on that you can check out if you're so interested. And basically what I'm saying is, if I look at the ratio of the terms in my series, if one goes to infinity and the other is just like a constant multiple of that, it's going to be dragged to infinity as well. So I'm going to look at the ratio of the terms as I is going to go to infinity. I'll bring the 1 over I up and combine it into a simpler expression. And then as the I goes to infinity, taking that limit, it's just 1 over p1 to pn. It's a number, it's a finite number. And so the limit comparison test works. And indeed, we can say that the series on the top behaves like a harmonic series. A harmonic series we know diverges, and this gives us a contradiction. We're saying that the subseries diverges, but the subseries is smaller than the main series that has even more positive terms in it, and the main series, the x plus x squared plus x cubed series, that converges. So the contradiction that we get is that a divergent series is smaller than a convergent series. That's impossible. And this establishes that the original claim that our reciprocal prime series converged must be false, and so we conclude our reciprocal primes diverge. Let me show you a couple more things that I can do using Maple Calculator, the sponsor for today's video. Suppose I enter a function like x sine of x. Immediately I get a beautiful plot that I can zoom around on, but what I really like about Maple is it contextually interprets the type of mathematics that you put in and gives some helpful list of possible things you might want to do, like take the derivative of x sine x or the integral of x sine x. But what I really like is you don't just get an analytic solution. If you click the steps button, you get these step-by-step solutions that tell you how to do the integration by parts to be able to evaluate the integral of x sine of x. If I put in a matrix instead, then the contextual manual of options are going to be things like row operations and eigenvalues and so forth. As a math professor, I'm really a fan of using technology to support but not replace our learning of mathematics. And that's why I think having a really quick way to do routine but relatively cumbersome computations or to verify your work as you're trying to learn this is a really helpful thing to have, and why I'm proud to be sponsored by Maple Calculator. So check out the link down in the description to install for free the Maple Calculator app, as well as the link to their browser-based Maple Learn. If you have any questions or thoughts about this video, put them down in the comments and we'll do some more math in the next video.